So let's warm up to the task of privacy amplification by considering a simple example. So remember the setup. We have a string x, which is a n-bit strings, takes values in 0, 1 to the n. For the purposes of this example, I'll assume that x is uniformly distributed, which I'll write using a little r here, completely uniform, but the eavesdropper has some side information about the string x. And here, for the example, the way we'll think of this side information is that the eavesdropper simply has stored as side information some of the bits of x, p times n of them, where p is some number between 0 and 1. So this string x, you can write it down as x1, x2, x3, etc. up to xn minus 1, xn. And think of the side information as being either a blank symbol when the bit x has not been stored, or a copy of the bit. So for instance here the eavesdropper has x2, does not have x3, etc. Maybe it has xn minus 1 and does not have xn. Right? So it keeps pn of the bits in this way. Alice and Bob know that the eavesdropper has stored pn bits, but don't know which bits it has stored. And their goal is to come up with shorter strings, Ra and Rb, are identical and are as close as possible to uniformly distributed from the point of view of the eavesdropper. So how do we do this? Well, in this case, one thing that would work is, simple thing, take the parity. So what if you take r to be equal x1 plus etc. up to xn? Then the eavesdropper has a subset of these bits, but as long as the eavesdropper doesn't have absolutely all the bits, it means that one of these bits, for instance in my example it's x1, is random, and you know that if you take a parity of a bunch of bits, as soon as one of them is random, then the parity is random. So this is going to work as long as p was not 1, because if p is 1, the eavesdropper has stored everything, there's nothing we can do. Okay, but this has one drawback, which is that we're only extracting one bit here. So can we do a little bit better? Surprisingly, it's very hard to do better. You'll see this in the problem set if we consider only deterministic schemes. And this is something we saw earlier. We know that there should be some randomness involved. Here it's actually not clear because I'm considering a restricted type of side information. But it is in fact the case that we need randomness in order to extract more than 2 bits. So let's see how we could do it. Here's an idea. We're going to choose random strings y1, ym at random in 0, 1 to the n. So this is something that Alice is going to generate on her own, and she's going to ship over to Bob on the public communication channel. And then what they'll do is that they'll set r to be the dot product of x and y1, and then the dot product of x and y2, etc. up to the dot product of x and ym. This way you get an m-bit string. And the question of course is whether this is secure or not. Is it the case that with high probability over the choice of these random strings, y1 up to ym, these bits x.y1, x.y2, x.ym look uniformly random? So you can show that this is the case, and this is natural as you don't try to get too many bits out of the procedure like this. So how do we argue that this looks uniformly random? One way to think about it is to generalize our perspective on the eavesdropper side information a little bit. Think of it not just as fixed bits, but think of it as just linear equations. So for instance, the fact that E contains x2, this is the same as saying that E contains the dot product of x and the vector which is 0, 1, 0, 0, 0, 0, 0. So if we want to show that, let's say, the last bit output by our procedure appears uniformly random from the point of view of the eavesdropper, we want to say that the distribution of x.ym, let's say the probability that it's equal to 0, this should be as close as possible to a half when x is chosen to be a uniform n-bit string, and if we fix m-1 plus p equations in x. Because what we have here is that we have x.y1 equals, let's call it a1, etc. up to x.ym minus 1 equals am minus 1. And we also have as side information x dot, in the case of my example, e2, where E2 is this vector that just has a 1 in the second position, equal to a certain value, x2, and then we have p of these. So that's all the information that's available to the eavesdropper if it's trying to predict the last bit output by my procedure given the m-1 previous bits and the side information that it has stored previously in E. Now, what is the distribution of this? Well, here we have m-1 plus p linear equations, and these they specify a 2 to the n minus number of equations m-1 plus p dimensional subspace of 0, 1 to the n. And so this conditioning is equivalent to saying instead of choosing x uniformly random over the whole space, we're taking it uniformly random in that subspace. And x.ym, as long as ym is linearly independent from the equations that we have so far, then this bit is going to be uniformly distributed provided the subspace is not empty. So from all this, what you can figure out is that this is going to be epsilon s secure for some epsilon s, which is going to be roughly equal to the dimension of this subspace. So a half to the n minus m minus 1 plus p. And so you see that as long as m is less than roughly 1 minus p times n, which intuitively is correct because this is the number of degrees of freedom that we have initially, right? There's pn bits that are fixed by the eavesdropper side information, so there's 1 minus p times n bits that are free. And here, as what we're saying is that as long as we try to extract less than the number of initially free bits that we had, then the procedure is going to be secure. The string is going to be secret from the point of view of the eavesdropper's side information. So here I gave you a heuristic argument why this bound should hold, why the procedure should be secure as long as m is roughly less than 1 minus p times n. In the problem set, you'll work this out into a little bit more detail. That's our first example of a concrete privacy amplification procedure that is able to extract as many bits as is possible from the weak secret x, depending on how much side information the eavesdropper has. Of course, here we made the assumption that the eavesdropper side information was a little bit specific, and so what we're going to do in the coming modules is describe procedures that let us achieve the same task, but under no restriction on the eavesdropper side information, aside from the fact that it's not too large, so in the sense that there is some entropy left in the weak secret x that Alice and Bob share, conditioned on the side information.